TD Gammon has some weaknesses, and so the use of neural nets in the gaming field calmed down and remained with hobbyists. It took over 2 decades for the next major advancement. That would be thanks to DeepMind's breakthrough on Atari games. Like TD Gammon, it works by feeding in state information into the network. In this case, the state is pixels on the screen. However, there were a few key insights that helped it excel in the Atari environment. Insight number 1, the loss function. We're still going to use our old friend, the QUpdate function. Instead of using it to update a QTable cell, we'll use it to directly update the weights in our network. Our new Q function will now take 3 parameters: a state, an action, and the weight of our network. Our learning rate from before? Easy. It's the same as our learning rate for the neural network. The final layer of our network is going to have a node for each action, and is going to estimate the Q value for each of those actions given the state fed into the input layer. So the result of this function would be the label we're trying to predict. On the other hand, this part of the Bellman equation value with the state prime is the data we'll be fitting against. So if you look back at our simulation cycle, in each term we get a state that we were in before we took an action chosen by the agent, a reward as the result of that state in action, and a new state, or state prime, as the action is complete. This gives us everything we need to train. We'll start by feeding state prime into our network. That will give us the predicted Q value for each action associated with S prime. We'll take the maximum value prediction and use that to calculate our label, which is the max value times our discount and added to the reward. When we prepare our label to be compared against the predicted value, we only want to update the output node corresponding to our chosen action. In this case, the chosen action had an index 2. So index 2 has our calculated future value, and all other output nodes get 0. Finally, we'll feed in our state to see its predicted Q values and backpropagate based on our label. Let's take a look at our update function one more time. If we replace these terms with their more commonly used symbol, and then take the integral, we get our old friend, the root mean squared error loss function. That means we could set up our neural network just like we would for a supervised learning problem, and use all of our favorite libraries. The majority of the work is transforming the data before fitting.